Hello and welcome again to Static 2400. Today lecture will cover two sections, 5.3 which is the equations of equilibrium, and also 5.4 which will talk about the special object which is members. We'll take some examples. Now the equation of equilibrium that satisfy an equilibrium of a rigid body consists of three equations. The first one is all the forces in X and all the forces in Y must be equal to 0, and these are the two minimum equations required for equilibrium of a particle. But if we have an object, we require that the moment about any point O, and this is within the object, must be also equal to 0. Let's take this example. We have a beam supported at two ends. One is simply supported with a roller and the other is pinned. This means drawing the free body diagram will lead to. Now, drawing the free body diagram involves labeling all the dimension and also the magnitude of known forces, as well as identifying the unknown reaction forces. For the pin, we have two reaction forces unknown in X and AY, and you can see here I chose my coordinate system to be positive X to the right and positive Y upward. Also, notice that I chose my unknown to follow this coordinate system, so X to the right and AY upward, as well as the reaction force normal at the roller perpendicular to the surface over here, so it's Py. So we have three unknowns. Now applying the equilibrium equation will help me find these unknowns. Applying all forces along x-axis, we have only one Ax to the right. All the forces Ax plus nothing, because we don't have any other force, is equal to 0. This satisfying equation 1. Equation 2, all the forces in y equal to 0. Now we have Ay positive up minus 10 plus By, which is also unknown, equal to 0. And the last one is a moment. Now the choice of the point where you want to calculate the moment is up to you. You always choose the point where you simplify the problem. Now most of the forces we have here is at A. Typically we choose a point where majority of forces are unknown. This will reduce the amount of calculation. So in this case I will choose A to be my point where I'm calculating the moment. Summation of all moment about A. Now I'm choosing the right hand rule, positive clockwise or counterclockwise, so that's a positive, so counterclockwise, and this will help me identify the direction of that moment. So calculating the moment of Ax and Ay about A is 0 because it doesn't have any distance. The moment of the force 10 Newton, it's clockwise, so it is the distance multiplied by 10, and it's negative because it's clockwise, so negative 10 plus the moment of By, which is distance, which is 2, multiplied by the unknown By, and its direction is positive because it's going counterclockwise. So we have three equations with three unknown, and that will be used to solve. Now automatically Ax equal to 0, and from these two equations, which we have Ay plus By equal to 10, and we have also from the last one, and you can see from the last one automatically we can calculate By, so 2By equal to 10, so therefore By equal to 5 Newton, and the direction of that is positive, meaning that our choice of Py is correct. If you got that as a negative, then it should be opposite, so this is upward. because it's obtained positive. Now let's examine the second one. So I substitute 5 in the first on this equation, which is 2 prime, right? Substitute here, and you're gonna get ay plus by 5 equal to 10, then ay equal to 5. Again, this is upward. Right, so this way we solve the equations. Let's take this example. We have a beam. It's pinned in A, and at B it's supported by a cable. The cable has is inclined by the geometry given here 3, 4, and 5. A uniform force applied on that beam, a P, which has a length of 2 meters, and that uniform force is 3 Newton per meter. Also, there is a concentrated force at the end equal 5 Newton. We want to calculate the tension and the reaction force at A. So calculate reaction forces at A and tension, cable tension. Great. So step number 1 is draw the free body diagram, establish your coordinate system, and label all the forces. So first of all, I choose my positive coordinate system. This is counterclockwise to follow x positive to the right, upward positive, counterclockwise moment positive. And I replace this uniform force with a single force acting at the center, because this is a rectangle, and its location is going to be in the middle. So this is going to be 1 meter from both sides, right? 1 meter. And we have also tension force. This is 5, 3, 4. We have a concentrated force. It's 5 Newton, and that's single force over here. It's simply 3 by 2. That's gonna give us 6 Newton. Now we have unknown, also reaction force. This is pin. We have 2 forces. I choose them to follow my choices, the coordinate system, AY and AX. So the unknown are AY, AX, and also the tension. Now the order of the equations matters in the such it makes it easy sometimes if you choose which one to begin with, especially with the moment. Now so the objective is to make our problem easy to solve without going off back substitution to find the unknowns in these 3 equations. Now if I choose that my summation of moment to be calculated, for example at point B, right, then I will cancel the moment of t because it doesn't have a distance. If I choose it to calculate the moment about A, right, then also it will cancel AY and AX because the distance is 0, but it will involve a t. So in whichever way you want to calculate it, it's gonna help you find the unknown. So I'll try to calculate the moment about A, which is at this point. This will cancel the moment of AY and AX. So I will be left with the moment of the 6 Newton, which is gonna create counterclockwise, so it's a 6 by 1, plus the moment of the concentrated is also counterclockwise, so it's a 5 by total distance is 2, plus the moment of t. Now this moment of t has only the distance between, or the way I can solve it is decompose t into two components, ty and tx. So ty is going to be t multiplied by, right, 3 over 5, and tx is going to be equal to t multiplied by 4 over 5, right? So this is ty and tx. We know that the moment of tx equal to 0, therefore the moment of ty should be only considered. So plus, now the moment of ty, because it's gonna generate a moment which is counterclockwise, is gonna be positive. So I apologize, these should be negative here because it's clockwise. So this is t by 3 over 5 multiplied by the total distance 2 equal to 0. So we have one equation with one unknown. So therefore t is equal to, so this is 5 over 6 and multiplied by summation of these two, which is 16, right? So that's going to be in Newton. Now you can apply a summation of forces in x equal to 0 that help you to determine how much ax. You have ax, which is unknown, plus, now plus tx, which is t, which we already found. It's 5 by 16 over 6 multiplied by 4 over 5 equal to 0. So therefore ax is going to be a negative value of 4 over 5 multiplied by that magnitude. Negative mean is this way, opposite to our assumption. So here we're assuming this to the right, so this has to be to the left. That's the meaning of it. The last one is summation of y equal to 0, and that's simply will give us the following: ay minus 6, right, minus 5 plus the ty, which is the magnitude we found, 5 over 6 by 16 multiplied by the angle 3 over 5, and that's positive equal to 0. Therefore ay simply is 6 minus 5, 11 minus this magnitude, 5 by 16 by 3 over 6 by 5, right? That's in Newton. Alright, the next section is 5.4 is 2 force members and 3 force members. The objective is to simplify the problems in special structure shapes, and that's going to play a significant role later on when we discuss the trusses. So let's discuss these 3 structures. We have a number that has 2 ends, A and B, and each end has a force acting on it. For this number to be stable or under equilibrium, the summation of the force vectors Fp and Fa must be 0. And this only takes place, in fact, when these 2 forces are aligned. along the line that is connected between A and B, conditional that there is no other force in between A and B that acting on that member. Examples where you can find members: hydraulic piston or actuator, A and B. I know this is part of this big structure and it's undergoing here reaction forces, but which can be summed in AX and AY as a vector A, and same thing as BY and BX as a vector B. What we will know that the direction of the forces at B and direction of the forces at A are similar, and they are along a line that connecting A and B. So they are along these two lines. So this greatly simplify problem and make it determinate. Let's take this problem as an example, and then we will discuss more problems. We have a cantilever or a beam supported by a hinge at A and a member DC. We want to find the support reaction at A and C. At A and C. Also, we can calculate the reaction force at D. Now, when we draw the free body diagram, you're going to draw the free body diagram of each component of this structure and see how the forces are distributed. First and for the most important part in the step is to choose our X and Y axis, right? And then we're going to draw the free body diagram labeling all the forces that we know and that we don't know. And if the force is a member, then we know that for that case C and D is a member, then the total reaction force as a magnitude and direction is along this. So let's see how this all happened, right? So on A is a typical hinge, so it has two unknown, AX and AY, and positive in this direction. We have also C. Now in C is similar to AX or to, let's say, CX and CY, but one thing about this hinge or this pin is directed along this member, and therefore the CX and CY as not as a component but as a vector has a total force that is its magnitude is FCD, and its direction is along that DC, which is 1.5 and 1.5. This makes a right triangle with 45-degree angle on here. So in this way we have only three unknowns, FCD, AY, and AX, and we can obtain three equations from the equilibrium. So this problem is determinant. Determinant means that the equation of equilibrium, which is moment and forces, are sufficient to calculate the unknown. If the number of unknowns are more, then it's indeterminate. Now the next step, I think all of us are familiar with it, is choose a point to calculate the moment, and we choose here point A. For the point A, the moment of the force AX and AY is 0. The moment of FCD is simply FCD sine 45 multiplied by the distance 1.5, and the moment of, and that is going to be clockwise or counterclockwise, so it's a positive. However, the moment of 4 is going to be counterclockwise, right? So it's going to be counterclockwise like that, and this is clockwise. So this is counterclockwise is positive and clockwise is negative. So this is 4 is going to be multiplied by total distance 3. That's going to be giving us the moment of A. And from that we have one unknown. Calculate, we're going to get that force. Next is apply the forces in x and forces in y. Scalars again is equal to 0. Start with summation of forces in x equal to 0. This simply boil down to negative, or I'm sorry, ax plus FCD cosine 45. So this is the component, right, of FCD. So this is going to be FCD cosine 45, and that's it, is equal to 0. Therefore we can calculate AX, right? And negative mean, our choice of our direction here should be flipped the other side. Lastly, AY, similar fashion, gonna get, you know, the negative value, meaning that the correct value or correct direction is downward. All right, let's talk about determinant and indeterminate systems. We said a determinant system is a system that can be solved using the equation of equilibrium, and there are three for coplanar problems or 2D problems. Now, looking at this first quiz, how many support reactions are there, and is the problem statically determinate? Well, we have here one reaction force, a normal, another reaction force 2, and a third one, right? We have 3, right? Now 3 unknowns. A second question, is this problem statically determinate? Well, we have three unknowns and 3 equations that we can abstract or can obtain. Now here's the thing. If we obtain the free body diagram of this problem and look into how these forces are arranged, we have normal reaction force at each of the roller, normal. Now, one thing about this problem is not even under equilibrium, simply because when you apply the forces at x, this force has a component, and there's no reaction force that stop this from moving. So, not static problem, simply because this cannot be 0. This cannot be 0 because there's no reaction force from here that oppose that. These are normal, right? Second, even if we suppose that there is some kind of another roller here, let's say there is another roller which stop this from moving, right? But let's not put that here. Applying the forces in y will lead us to one equation with 3 unknown. Applying moment about any point here, and we can choose, for example, A, B, or C. Let's say I choose here A, will lead me with another equation, which is gonna be equal to, if I choose A, right? So 1, 2, 3. So let's write this. So I'm gonna choose this is to be distance A, distance B, distance C, distance E, distance F, whatever, right? In that equation, when I write it about A, I'm gonna have known moments of these forces, and let's say this is the moment of all the forces, right, which we know. But there's also moments of 2 forces which we don't know, because By and Cy are unknown. So let's say plus some constant C1 multiplied by B1 plus some constant C2 multiplied by Cy, right? And this is equal to 0. So we have 1, 2 unknown, and that's it, right? That's it. So we have only two equations with three unknown. Two equations with three unknown, right? So this is not sufficient to solve. The problem is summation of fx not equal to 0 did not help us. So therefore, the answer for the that problem, going back here, is D. So yes, although we have three equation, three unknown, but it's statically not determinate. Let's examine the second problem. Says we have a beam loaded and supported. How many support reactions are there on the beam? And second, is this statically determinate? And C, is the structure is stable, right? So let's examine that. Well, this structure A and B is fixed at A, so therefore it has a three reaction force. One AX, AY, and the moment to counter this moment coming from the weight and loading. So we have three unknowns here. Also, we have additional support, an extra support that is connected to this beam, and the reaction force at this point is gonna be along the beam direction, right? It's gonna be along the beam direction. So what we get is another force here, unknown. So this is, we call it of the member, and we have here also AX, AY, and also a moment. So 1, 2, 3, 4. We have four unknown reactions. We have three equations we only can obtain. So it's statically undeterminate, right? Now, is this structure stable? Yes, because it's sufficient to have a support at one end, and this becomes an extra. So this is over determined, right? So the answer for this problem is B. For equation, it's not statically determinate, and yes, it is stable. Well, let's take this problem as an exercise to do at home, and you should try it. But let's discuss that. We have a beam supported by a roller, and it's pinned on B. We have three unknowns. If I choose Y up, X right, we have BX and BY, and we have here a normal, right? A normal. Now the normal direction of that force is known with respect to my coordinate system that I choose. Let's say I choose this is my X and this is my Y. And this has become important, the selection of the coordinate, because as you know here, the force is different orientation from the forces here, right? Let's say this is your force upward and down. Now, the question is how to calculate the reaction force in the easiest way. Before everything else, we chose Y and X as seen here. Let's actually scroll to the second slide. Force reaction force is normal. We replaced the normal or the distributed load with a single equivalent force acting at the center of this rectangular. So it's a 3 by 4, it's 12, and its location is the center, so it's 4/2. Second, we want to calculate the reaction force at A. Now the easiest way to calculate is to select a point where you cancel the effect of the forces coming from the other unknown. Choosing the moment about point B will cancel bx and by and leave one equation with one unknown, which is NA. Now, to calculate that a moment, I need to calculate the moment of 12, so and a moment of the NA. So the moment of the 12 is going to be counterclockwise, so it's 12 by 2, plus the moment of the NA. Now, at the moment of NA, I have to be careful of how to calculate that. We need to know the total distance, distance from a parallel. So if we extend that over here, and I'm going to extend this, I want to know the component of NA in the y, which is NA cosine, so it's NA cosine 30, right? So this is NA cosine, plus the distance from here to here, the normal distance, right? So that distance is simply 4 plus, well, this is 3, from here to here is going to be cosine 30 is this unknown over 3, so therefore it is 3 cosine 30, 3 cosine 30, right? Cosine 30. So the total distance is 3 cosine 30 plus 4 multiplied by NA cosine 30, and that's going to be what? Negative, because it's clockwise, and that's going to give me the moment of this unknown, right? Okay. Now, does the second question, does the component of NA in the x direction has a moment? Yes, indeed it does. And this is the moment coming from this NA, right? NA sine, I apologize, I don't, I'm not using my pad here, but you got the idea. So that component is NA sine 30, and it does have a moment because it has a distance from this point, and that distance simply, it's 3, so this height, I mean this is the height, right? So it's a 30 sine 3, so this is 3 3 sine 30, right? So 3 sine 30 multiplied by NA sine 30 is going to give me a moment for this component, and that component again is clockwise, so it's a negative, right? So I have negative. So overall you're going to have a moment for this NA, and this will directly give you the moment about A, and we will be able to calculate the reaction at A. The remaining unknown follow by applying the equilibrium at x and y. Simply after knowing this, things will fall easily and follow easily, and summation of forces at x, bx, which is negative, we assume here is a negative direction, plus NAx, which we calculated to be that magnitude, and it's a positive, it's going to be equal to 0. You can't calculate bx, and similarly by is going to be equal to negative 12 plus NA cosine 30, where NA 3.713 plus by equal to 0, you can calculate by. So the final solution is that.